As introduced, I'm Mehdi, a PhD student of Technical University of Munich in the computer vision group of Capture. And my topics are on pose estimation and point cloud processing, and kind of also using graphs for that. So this is going to be the contents today. As Peter mentioned, feel free to interrupt me whenever you have questions. I don't know if I can see if you raise your hand or if Peter reads it and reads them out. It's all good.
Yeah.
Otherwise, I feel like I'm the only one talking. But yeah, it's going to be good if we have also some discussions. So first of all, so this is the agenda for today. I will talk very briefly about different 3D data representations. Then I will talk about how to describe point clouds using graphs, and then using graphs to do matching, and at the end a brief conclusion. So what are the different 3D data representations that you can use for machine learning? I thought this would be interesting, as I'm not sure how much people are familiar here with different representations, but this would make a good storyline why graphs are interesting. Talking about different representations, we can start with like a very simple 2D multi-view, which is basically an older, like one of the first approaches to process 3D data, where you can render or you can have multiple acquisitions of a scene or an object, and you can use CNNs to process them. And you can do, for example, a view proof. This is the good thing about here, that you can benefit from 2D CNN, which there is like quite standard networks that you can use out of the box. And but this is very expensive in terms of setup, and also in terms of applications. It's very restrictive. There are many different papers initially, like a bit like older papers that process point clouds to do classification, to do segmentation from multiple view, and also reconstruction. Another way to represent 3D data is using depth map, or a combination of depth and RGB, where you do not have essentially a 3D volume, but you would have more like a 2.5D, where you have a range image, which can be the depth image, which represents how much close to the camera or the sensor you are. And this is also, again, because it's image-based, you can use or utilize those very powerful CNNs. And it is also very useful because a lot of cheap sensors are available even on mobile phones. But the problems here is that the data normally are very noisy. So normally given different technologies, these sensors are quite noisy and they have a lot of artifacts. And also, if you want to have a 3D view of the objects, you need to have multiple acquisitions. So depth maps have been combinedly used with RGB in many tasks, such as, for example, here on the top, you see they have been they are quite used in object pose estimation, where you stack a depth map on top of an RGB map, and you can do, for example, here a very fine pose estimation and object classification. You can also use depth maps for other tasks. For example, here, this is a work that they use semantic completion. So not only do a reconstruction of the scene using the depth map, you can also do more like and complete the missing sides of the objects. But then another different representations for 3D data is voxels. Voxels are, like, as you might know, they're like occupancy grid, which basically represents the data in like a 3D grid. And you normally need to subsample your data in order to fit to this voxel grid. And you can use 3D concepts, CNN concepts again, but in a higher dimension in 3D. As you might imagine, these might come a bit expensive because like having a higher order of like convolutions, this might be increasing in terms of memory. And there's also other problems with voxels, for example, how to integrate color information, how to assume which parts are occupied or not if you have a scan. There are like some also rather old works, like these concurrent works, which one is VoxNet and the other one is 3D ShapeNet. They try to represent an object here in using voxels. For example, here you see like 3D point clouds, and they convert it to occupancy grid, and they also have convolutions, a couple of layers, and then fully connected, and you can do classification. And very similarly here on the 3D ShapeNet, now it's a very famous work because of the data set, but you can also see here that they also presented their 3D CNN basically. These two methods are, like, as you see, quite very low resolution meshes that they represent using voxel grids, and they can do classification or other tasks as well. This is essentially how 3D CNN works, where you have a voxel occupancy grid, you have a 3D CNN, and then you apply it over top, and then this is the output of your CNN. In PyTorch, you can do this simply with a conv 3D, and you can basically define what is your kernel size for the 3D convolution. But if you look at convoxels, they have here, you can see that because of the discretization, you are missing a lot of fine features. Like if you want to do fine tests, this is a problem. There are some methods, of course, that they're trying to deal using octree, for example. They break down the surface into using octrees, and they represent it in like a semi-fine representation. This is one way to also process, still use voxels in a more optimized way. But as they introduce some complications, how to do the octrees, they're not very much used. A different representation, which would be the focus of today's talk, is point clouds. Point clouds is a different way of representing the scene. It can be an object, it can be a scene. It's basically a list or a set of points represented by their coordinates, basically x, y, z per point. And you can also combine color data. You can combine also normal or any other features you can stack on top of this coordinates basically. And this again can be applied to objects and scenes. But the problem with point clouds is that they are unordered data. What does it mean, unordered data? Assume you have a set of points. You can basically order them when you want to store them in a memory, or if you want to process them with such an order 1, 2, 3, 4, and each is represented with the coordinates, and this is your array. The same points, you can shuffle them, and it would be the very same points, but you would represent them differently. This means this you can represent with a set its order invariant. And this is not applying to standard convolutions, which they process ordered data, where order matters basically how you sort the data, how the image is basically formed. One way to process point clouds is using symmetric functions. And symmetric functions means that you can basically process points basically with a function that is applied to each point and does not take into account the other points. And also the same results would be achieved if you reorder the points. Such functions are like, for example, max function or add, where when you, for example, change x plus y, it's equals to y plus x. These are symmetric functions. And one way to process point clouds is using such functions, which is basically how is the first time they are processed. This is like simply using an MLP function. You can process each point and then increase their dimensions and do so up to you get to a higher dimension. This is how you can basically simply do the MLP using the conv1D with the kernel size 1. And this is basically how you can get to process point cloud using the so-called point net, which is the pioneering work to process point clouds, where basically you have start with endpoints, you apply some random transformations, and you apply some MLPs, which is the same MLP to all the points. And then at the end, as you do this multiple times, you get to some features. And here, in order to make a symmetric and do an order invariant processing, you basically can take a max pooling of this feature. And as you also reorder these points, you would get the same global feature, basically. This is how they manage to process point clouds to do classification. They also do, with some tricks, they also stack this global feature on top of the point level feature, and they do also part segmentation and semantic segmentation as well. So this is pioneering work to process point clouds. However, if you look at what PointNet does, is basically you have a point cloud and you apply every point a different MLP, and there is no shared information here. So basically there is no mutual features, there is no neighborhood information that comes to play, and it's basically every point has its own adventure. While here we can use graphs, for example, to take into account neighborhood information and take into account like more geometrical structures given these relationships of the points. This is why graph neural networks, or generally graphs, are good representations to process point clouds. So talk about how you can define these graphs. You can do a complete graph. You can basically connect all points together, which would be a complete graph, where you basically neglect their spatial relationships of the objects, and you connect them all together. You can take, you can build edges from these nodes. For example, as you might know, the nodes are the points in the point cloud, and the edges would associate them basically. And one way to connect or associate points is using like a spatial aware radius ball, where you basically connect the points that are closer than a threshold. You can also do KNN. You can connect points using such a K nearest points. You can connect the points, which is something also looks like similar to meshes. And this is also very easily you can do using like some functions from famous libraries with either with the radius like ball query, or using k-nearest neighbors. So this is about how to construct graphs, but you can also do more fancy things with deep learning. You can start with some points and have some point features, and you can also learn edge features basically. This is a famous work from Michael Bronstein's team, where they introduce edge convolutions, where you also learn some edge features, which can be used also to associate these edges, and also to connect the nodes. And after every edge calculation, you can basically do a message passing, which is basically defined by looking at the features on the nearby point, and then also taking into account these edge features, and then do an aggregation on top of this, on top of the local feature. So you can do a summation or any other function here. For example, you can take into summation. So you can sum up all the nearby node features, and also take into account like the edge features or the weights. And then you can basically learn and find a feature, and then stack it on top of the node level feature. So edge convolution is very famous, so you can also find implementations of it in PyTorch Geometric, which is like a famous library for processing graphs with PyTorch. And you can, as I mentioned, you can also find out what is the aggregation function you want to do. If you want to do max, you want to do sum, this you can change easily. So what edge convolution, or what this paper does on top of edge convolution, is they represent like how to connect points using KNN. And they basically do this multiple passes of this edge convolution. As you can see, the first layers, the connections of points, are very much spatially based. The first layers, you see, for example, to this query point, the red one, the closer points are connected. These are like the features are very close, which the first layers you basically design, you basically find the nearest neighbors in the spatial because you're using the coordinates. And as you go on, these features are more spatial, more semantic. And you can see that it kind of also, the nearby features to each point is representing its part, or like they're semantically meaningful rather than just being spatially meaningful. And this is how they also manage to do a good part segmentation. So these are the basis of graph convolutions. But here we want to use some concepts similar to the ones that presented for the task of point cloud registration. This is based on our work Graphite, which is presented in 3DV 2020. So what is point cloud registration? Point cloud registration is the task. It's a very old and classic computer vision task, where you have a pair of point cloud or 3D scans, and you want to align them. You want to bring these 2 point clouds together. That's what we call the registration. And the goal is basically to find a rotation and translation, which you can apply to the first point cloud, the source point cloud, to bring this to the target point cloud. So the goal is to find this rotation and translation. This is much used in a lot of different tasks in 3D computer vision, such as reconstruction, such as object pose estimation, camera pose estimation, even SLAM. And also it has also applications in medical, for example, data registration. So it's very much used, but how to do this is a bit challenging. So there are some classical methods, for example, ICP, as you might heard of. It's an iterative method where you take into account you basically try to register 2 point clouds using some closed-first solution where you take into account the point-to-point distance or point-to-plane distances. There are also similar concepts done in using deep learning. So you can also use PointNet, for example, features to do these iterations. Instead of doing like a mathematically driven closest form solution, you can also use PointNet features, for example, to do this. But these methods would fail because if you're initialized to a very bad pose initially, you would stop in a local minima, and these are very sensitive to initializations. And also, when you have partial scans, which is the case in real life, when you have partial scans, these methods might fail because their overlapping region is not sufficient to register point clouds. And this is where the local methods come to play, where you basically try to describe a local neighborhood with some handcrafted or learning-based features, similar to what we do with 2D, with SIF and SURF and those features. You have also equivalent feature descriptors in 3D in point clouds, for example, where you can use here, for example, there is a paper from ECCV 2018 where they use PointNet and also FoldingNet to describe a point cloud region. And you can use these features and match them with the descriptors and register the points without taking into account a global match. But this is one way to represent using PointNet, for example. You can represent a local neighborhood. You can also do, as mentioned, you can use voxels to represent or to describe a local neighborhood and have a descriptor and then match them to the register. And here we thought we can use graph-based descriptors to represent more structures and local neighborhoods than when these previous methods fail to bring enough power. And instead of also doing as previous methods, they do very sparse description. We try to make a more dense description where not only you learn a description, but also you learn some key points where you can utilize to do a point cloud registration. So this is basically different ways. So you basically want to, given a local neighborhood, you want to learn a descriptor vector, which this vector or feature can be used for tasks, for downstream tasks such as registration. So how does our pipeline work in a nutshell? We have a point cloud, for example, of here an object. We break it down into several patches, very small patches, and we want to describe each of them. So we take the points from each patch, we convert them to a graph. Here there is a graph where, like that, as mentioned, the nodes would represent the points in the point cloud, and the edges associate these point clouds points given their spatial relationship. So the point features, so the information that are laying on top of these nodes are coordinates plus some features, which can be normal, which can be color if it's existing. And the edge features are basically connected if you are under a certain radius. And there is also a feature laying on top of each edge, which is also kind of weighting how much these points are close together. So as you are very close, you have 2 points that are very close, they are weighted high. And if you have 2 points that are very far from each other, these values, this edge weights are lower. And this is our structure, or like our architecture, which we process to describe the point cloud or the local graph, where we have an input patch. We can compute the adjacency matrix, and this is the feature matrix of the nodes. And then we have multiple iterations of GCN. A GCN here is basically a matrix multiplication, where you can basically, this is like a simple matrix multiplication, where you apply it on different hops. And what hops, it means that how many layers, how many iterations these features can propagate. You can basically see as here, the hop is 1. A feature would travel only to the nearby, to the only one, to the nodes that are connecting to the original node. And if the hop is 2, this feature is traversing to the nodes that are having a distance of 2 to the originating node. And this is also for tree. So you have multiple iterations of GCNs with different hops. And with hops, the intuition is that you can capture more scale, multi-scale features, and not only having very small message passing, but you can also do a high-level scale of message passing. And you get some bottleneck here, and you can basically describe this. You can basically calculate a scatter max, or basically a pooling over these features, finally fully connected, and you get a descriptor here. But this is not the only thing that this graph neural networks can enable us to do. We can also extract some key points. So basically, we do the inverse of the first 3 layers, and we get to some value per point, basically, or value per node. And this value can represent how salient or how distinctive this point is. And then this can be used as a key point, basically. So basically, these values we have per point, and then the maximum can be taken into account as a key point. Plus, we can also learn some confidence value or score value, which represents how good, how distinctive this patch, this local patch is for the tasks such as, for example, registration. How we train this? We train them using triplets. First, we train them with synthetic primitives, which is basically some synthetic geometries that we generate, where we know where are the corners. And these corners, we give like a starting point to warm up the network and to derive them to extract key points as like the corner points. And the triplets, as you see, this is the same shape on a different sampling in the anchor and positive, and the negative one is a totally different geometry. It can be different like a shape, it can be different corner. It's also a corner, but it's a different one. And for another data set we train on, which is less supervision, as you have also with synthetically generated, and we do our actual training on, is ModelNet, where you have synthetic CAD models, and you can also sample point clouds on them. And then you can basically do our graphite pipeline to break it down into different patches, describe them, and then also build these triplets. The triplets are like here, you have the original or anchor patch. You can, with the pose, with the ground truth pose, you can go from the first patch to the positive sample, and you can also sample a negative basically sample to do the triplets. And for training, we have a Siamese or contrastive learning, or like a metric learning, where the graphite is describing each patch. And also it gives also some values, where in the initialization, we have supervision. As you'll see here, and this is for initialization, we know which points are the key points, so we can supervise them using L2 distance. The same with the score, which is like a score of the patch. And the descriptor would be formed using a triplet loss. This is a form of triplet loss, which tries to basically make the distance of the anchor and positive sample, the descriptor, close to each other, and also at the same time tries to make the distance of the anchor and negative sample as far as possible. Later on, we have some pose variation. As you see here, we have apply a pose to an object, and we want to learn without such supervisions that we had during initialization. Here, we basically form only triplets. So for detection and for the description, we use triplet loss, and there's no basically supervised signal here. At the end, how if we train this, this is, for example, a sample from the ModelNet dataset, where you have, for example, an airplane, a car, or a human, and you want to match these point clouds together. We apply our graphite pipeline. We describe each point, each patch, and then we match the closest points in the descriptor space. And then we try to do, we do PMP, we do pose estimation and ransack, and we get to this such pose, basically. We can further apply an ICP to refine such. As mentioned, ICP is very sensitive to the initialization, but if we drive already our point clouds to a good initialization, the ICP can even further fine-tune such results. These are results on ModelNet registration, which is already a bit outdated. Our method also works quite well under noisy data. We apply some further noise. And we also benchmark our descriptor on a famous 3D match registration benchmark, where you have scans with real scans captured with Kinect sensors. These are how our descriptor sees the space These are the C points, and this is basically a low level or like a reduced dimension of our descriptor. And you can see like it kind of has a different color in different in complex regions, basically. These are the scores of the key points. As you see, the flat regions do not get good scores, while the more complex regions get a higher score. And these are the validated key points. Basically, given this key point scores, we can validate our key points and get to more stronger key points for registration. And this is, again, the key points in the first frame and second frame. And we want to register these two, and you can see this is the registration outcome. These are results with on this data set. We managed to get the best results without even training previous methods. Train on this data set. We only train on synthetic data set, and we managed to get a good results on registering on this real scans. Next is a further extension of this work. This is just accepted at NeurIPS 2021. It's not yet.
Maybe if sure. We're passing to the next one, maybe a couple of questions.
Sure.
I don't think we talked about it, but maybe I missed. I always like to ask about training times, what hardware you use, inference times, what size of the data set. Is it categorized data sets or not? Is it free form data sets as well?
Yeah, that's a good question. So so in here, there is not so much of expensive training. So the description of the network, like a forward pass, is quite fast. So you can describe full scans with, I don't know, 500 patches in order of milliseconds, basically, because it's basically a matrix multiplication, a couple of matrix multiplication you need to do. So that's why actually the graph-based description is actually quite lightweight.
Yeah.
In terms of training, this data set, I think it's like around a couple of thousand synthetically generated data set. And this ModelNet data set is quite small. So per instance, for example, for car, you might have 100 instances. So if you train on a car, you only have 100, for example, car shapes that you can train on. And we got calculator results with training, for example, on instances of on, for example, category level. For example, you train on 20 different shapes, and you train on other 20. So this means that the network has not seen such categories. So it's quite lightweight, I would say. It's not very hungry, and that's. However, in real scans, we do not train on real scans, as mentioned, but a description of these as like you have much more seeds to play with. Depends how much you want to do a fine level registration, and so you can sample as many points as you need, basically.
Okay. You mentioned a couple of like sub-second. This is on home PC style, or is it on the cloud?
It's basically on a GTX with
1000 some hundred.
Yeah.
Okay.
It's not. I never tried it actually on the CPU, but one can also try it on the CPU. I think it would not be so much memory hungry. The only problem here with graphs, I see like the processing of neural networks is not very hungry, but the how you associate the points in like with KNN, for example, if you want to build the graphs, those are the only parts that even takes more time than the actual forward passive network. Here we do not do KNN, we do bulk query. But if you want to look in the neighborhood and if you have a huge point cloud, this might come expensive. However, we do not do, we only subsample, for example, we only do look for near points in like a scale of, I don't know, 1,000 points or so. So it's not very, but if you have a huge point cloud, for example, lighter point cloud, and you do not want to subsample them and describe them all, that is a challenge basically to find the nearest neighbors.
I actually have a question, might not be fair one because you might not have all the information, but the new iPad, I think an iPhone, they have LiDAR scanner and 3D reconstruction and everything in it. This type of architecture can work on an edge device as an iPhone, iPad?
I would say so. It's very lightweight actually what we do.
Yeah.
It's as mentioned again, it's like a simple matrix multiplication over like your graph adjacency matrix.
Mm-hmm.
So it's only the matter of how many points you want to put into this graph. If you want to describe like have 100 seed points, it's very efficient. You can describe them in some milliseconds. But if you want to describe like the whole scene, very fine level, and not to miss anything, then it's challenging. Because you probably need to find you need to define your graphs using KNN, and if you have, for example, a GPU based implementation of KNN, it might improve. Here we do not use a GPU enabled KNN, but it's interesting to look at such problems and like to try if I haven't tried it actually, to be honest, on CPU, but we can also try it on CPU and see if there's how much is the runtime.
I have a question. Actually, I have two very technical questions and one more theoretical. I'll try to be very concise. The first one is, how do you initialize the patches? You said that you're choosing the patches in the beginning of the description of your work. Is it like the same of PointNet, the furthest point algorithm?
Yeah, so this is a good question. You can do furthest point sampling, of course, and we do furthest point sampling, but in training you do not need to use furthest point sampling. In evaluations, you want to make sure that you have you break down your patches to uniformly distributed patches. So what we do basically, we during evaluation, we break down the point cloud, as you mentioned, with furthest point sampling, and we sample, for example, 100 points, and then we find the closest points to these seed points, and then we can use the description. But during training, we can do even random sampling, because you do not need to make sure that, because we do patch level training, we don't do over objects. And with that constraint, you can basically do random sampling.
Thanks. My second technical question is, how do you choose the primitives and how you define the negative? It's not trivial to define a negative to a primitive. How do you do that?
Yeah, so basically this is a very good questions, and it can be also, you can put a lot of time on finding the negative sample. However, what turns out working well is like, so you can basically draw one random sample from as a negative sample. Here, we wrote some code in a 3D software where we have a meshes, and this the deformation is changing the number of edges or faces that are building this corner are changing in a range.
So this is some kind of a deformation distance?
Yeah, basically. So there's different deformations, different curvature, basically. And this curvature is quite important, basically. And we try to basically randomly draw some negative sample. It's very trivial in this case. And it works quite well because you need to, maybe sometimes it might be very similar, as you, for example, see here. But this can be considered as a hard negative. And this is actually quite good to train with some hard negatives, which are very close to your positives.
I suppose this is the equivalent of finding lines in orientations in 2D convolutions and corners and stuff like that. So yeah. I would like to move on to my third question, which is more theoretical. I understand that you try to apply like the transformations to register point clouds that are of the same shape, maybe. Or did you try to do deformations that like affine transformations were required, where you could apply this method for, I don't know, motion capture?
That's very good question. Here we have some samples, as you see, with scenes where you have it's not the same shape; it's a different sampling. But getting to your question, yeah, this is actually what we are extending our method to meshes and
This is your
deformable
next work.
surface. Yeah, I actually don't have it in the slides because it's not yet published. But yeah, we are actually having this also as a next version to try, because with graphs you can also actually capture surface level information and deformables. So that is actually also, I would say, working quite well.
I will definitely stay tuned since this work was really fascinating. Thank you very much.
Welcome. Thanks for the questions. Okay, is there any other questions?
On YouTube, no, I see no ones in chat. I think we'll continue.
Okay, yeah, we can also ask it after this one. This is a bit shorter. This, as it's just accepted to NeurIPS, and the idea here is to bring graphs for matching and also to scene level registration, where in Graphite we try to describe local patches of shapes of, for example, CAD models. And the idea is to do a coarse-to-fine matching. And initially we have some coarse matches, we describe them, and then the next layer we have a fine level matching. Here the pipeline is a bit different. You have one pair of point cloud from different scans. You can use a Siamese network to describe these point clouds, and then you can sample. Here we use voxel-based sampling, which is quite used in actually this scene level registration. It's different than, for example, furthest point sampling, but it's much efficient, and it's basically making sure that per different voxel grid you have one represented sample. And we basically do a correspondence block, which I will present you shortly. It's basically instead of as in Graphite or other classical networks, you have a descriptor which can be handcrafted or learned, and then you find the matches basically in descriptor space. You have some distance, can be like a Euclidean distance, can be for example, cosine distance, and you find your correspondences like that, and then you do, for example, your post-estimation. Here we want to learn matching as well. So the correspondence means that we want to supervise on correspondence rather than supervise on the description or the descriptor. How this is done, basically, this is the correspondence proposal. Like you start with some points and some features associated. And we have two main functions here. One is contents aggregation using graph neural networks, and one is the optimal transport layer. What is context aggregation using GNN is basically you assume this is your scene and these are the sample points which can come into a graph for each scene. In the first level, we do a self-attention, which means that the points features would do like a pass, a GNN pass, and on each side, for example, the self-attention means that you would, on scene 1, the features would be traversing the graph with its nearby points on each scene. And a cross-attention means that you do this across scenes. So you basically have some meta connections from scene 1 to scene 2, and you can basically compute your attentions from scene 2 to scene 1 and the other way around. And this is two graph passes we do to basically find out attentions on each side. And the self-attention, the intuition is to focus on self-similarities, and the cross-attention, the intuition is to focus on potential matches. You basically find out your matches looking on the other side and with these graph passes. And then we do an optimal transport matching. I'm not sure how much you're familiar with optimal transport problem. It's a classical problem to match two sets or two distributions. And you can also have initial each cost for, you can build a cost matrix basically for each point to point, like a score or confidence basically. And there is this famous sin-Korn algorithm, which you can find a differentiable version of it, and this can solve the problem. Here, basically, the idea is that you have a score matrix. This is the score matrix is basically representing how much each point, each pair is in the descriptor space, the distance of the descriptor space you assign per point. So you have, for example, m point on the first point cloud, n point on the second point cloud, and you can basically find a score of point-to-point descriptor space. And this is your matrix, and you want to basically do this optimal transport to basically find what is the best match from scene 1 to scene 2 given this global information. And what it does is basically some passes of doing normalization. So it makes sure that every row is the summation of each row is 1, the summation of each column is also 1, and you do this iteratively. For example, you do perform this 100 iterations, and there are some dustbins or slack entries where you do not have any matches. And then you can supervise them using in the log space. You can also, with some weights that we have given the occluded regions or the overlapping regions, you can also assign some weights to the regions that basically are overlapping between two scenes. This is the loss function. So this is the first pass, and then the refinement stage is like the idea is that when you do a coarse level matching, you might miss to have the exact same point on the other side because you do some subsampling, which is using voxel based sampling. You might miss to have a representative point on the other side. And in order to circumvent this problem, we do a fine level matching as well, where basically we take the initial correspondences that we found out, we look at their neighborhood, and we basically describe, give these groups basically to a network to describe each patch. And these patches, each would be passed to a sin-Korn algorithm or to an optimal transport to find a local match. Basically, every patch is also matched across the equivalent or like the matched patch on the other side. And then you can find out every correspondence in a very finer manner. And then you can concat all these correspondences and find out your final refined correspondences. These are like the aggregation from very many different small groups of patches. And with this, we get two very good alignments. This is like what you have with the previous methods, which also based on attention and transformers. And this is our results with coarse level matching, and this is our results with fine level matching. As you can see, we have a very high inlier ratio compared to the previous methods. And these are our quantitative results compared to state of the art. You see on 3D low match, which is very low overlapping data set, we get very good results, and we have very good inlier ratios basically. And here you can also see number of parameters. The previous methods have much more parameters, and here we have like 5 million parameters too. And these are the results on other data sets such as autonomous driving and Kitty data set, where you have also a pair of point clouds and you want to register these scenes, and you get also pretty good results on this data set. So as a conclusion slide, as presented, you can see graphs can be used to describe point clouds quite efficiently, and they can capture more geometric and more they can encapsulate this neighborhood also into the features. They can represent also shapes or scene structures with like a scene graph, or with a shape level graph. You can represent, you can use graphs to represent scene level information. And then you can use GNNs to also learn matching across different scenes or different shapes using this self and cross attention concepts. So this was my final slide. Thanks for your attention. If you have any questions from any of these works, let me know. You can also write me if you had anything to discuss with me about these projects.
I have a technical one. Is anything open source so we could use?
So the plan is to open source both of them. So the Graphite actually is, I have already shared it with a lot of people, but it's not per se open source because we needed to also provide some pre-trained models, but the code is available. I think this is like would be open source in a couple of weeks, because it's almost ready, and there's like final things that we need to do. But if you want it right away, I can share with you.
Because I know there was a question regarding this. People were asking for the open source.
Yeah, this
is a recurring question for all of the talks actually that we have.
That makes sense. So if someone wants it right away, if they want to work on something, they need it for some works or so, I'm happy to provide the code right away. Otherwise, we want to open source it as soon as possible.
Once you open source it, if you could like write it or the Discord or the Reddit that is available open source, so people will probably like to see that. It'll
Definitely,
also go on the newsletter if you do so.
That would be, yeah, definitely. I can share it with you.
Yeah. That's for me technical aspects, but it's better if anybody has a more on point question. No, quiet. Let's see in the YouTube what's happening also there. But they're maybe in delay. No, they're not in delay. Guys, if there are no questions, we're wrapping this up. So we'll give you a couple of seconds to think if you have, and just let us know if you need to formulate it and you need some time. And in the meantime, I will repeat, I think we're reaching 2,000 subscribers in 1 year of operation. This is really amazing. This is a good chance for me to say thank you for everybody who participated today. Everybody will be seeing this recording. I know usually there's 10 more people watching. 10 times more people watching the recording than participating in the event. So I think this talk will be very interesting for many people. Mahdi, thank you. Thank you for, I didn't have a lot of questions because most was clear. That's on my end, I can say. Usually when stuff are not clear is when I start pounding in the questions. So thank you for this very elaborate talk today. I think I wrapped up basically. If you have anything to say, go ahead. Otherwise, we're closing.
No, thank you. Thanks, Peter, for invitation. It was a pleasure to present this. Yeah, definitely. If you have any, if you see this also recorded video, if you have any questions, feel free to drop an email. It's all good. Yeah. Thanks again.
I will add the recording will be published. Who was that? Sorry.
I just want to say thank you.
Sure. The recording will take about a week to publish. I'm in transit in the following days. Right now, I'm basically in Costa Rica, sitting in front of the Caribbean Sea, looking at the ocean. But I will be going home in 2 days, so it'll take a bit time to publish. Along with the recording, we will have, as usual, chapters for everything, so people could browse easily. And yes, again, thanks everybody for joining in today, and until next time. Bye for now.
Thank you. Bye-bye.
Thank you.
Bye.
I see there was a question for the Discord link. I'll send it again right now. You'll have all the links right now in the chat, but you can also find it in the meetup and everywhere on the YouTube. The links are everywhere, like in the Reddit. So don't worry if you didn't get it now, you just go on the meetup and you'll see the link there. Yeah, I will say bye for now.